Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll. The big news, I suppose, is that in fact I have given in to social pressures and cut my hair just a little bit. I mean, it wasn't even social pressures. I was not getting a lot of social pressures. It was internal pressure. Part of me, I will confess, had this romantic idea that one should just not get one's hair cut during the lockdown, during the quarantine, as a statement of, I don't know, solidarity or something like that. But there's a certain kind of hair growth that leads you to be kind of casual and rakish, and then there's a certain kind that at some point you just look like a mess. You just look like a slob. And I think I had crossed that threshold a little bit, so tiny bit more tidy today. Otherwise, we're continuing on. This is the Q&A video for idea number 10, which was interactions. Remember, we talked about quantum field theory. I'm not going to rehearse the whole thing again. When we had some free quantum mechanical fields, we showed that they were equivalent to sets of particles, and now we've turned on the interactions a little bit and we did scattering. So basically the picture was, I will redraw this again, if this is space, you imagine that there is some kind of little wave packet that represents a particle, the wave function for a single unentangled particle that you can derive from the quantum field. And there's another particle, and they're coming together. And then over time, that evolves into something much more complicated that we can't draw because it's a complicated wave function of many now entangled particles. But basically, there's going to be, if you observe those particles, then what you will see is, if you observe those quantum fields, you will see a set of particles moving out in different directions. So the left-hand side really represents the thing that is going on when you set up the situation in the first place. The right-hand side represents one possible observational outcome. And Feynman, in the sense of, in the case of Fineman diagrams, showed us how to actually calculate this. There was stuff that happened, but there were particles that were going in, and there's some particles that are going out, okay? I should draw 4 because I drew 4 up there. Bunch of particles going out. And there were details, and we talked about the relationship of these Feynman diagrams to the interaction Lagrangian. The Lagrangian is the way that you specify what your theory is, okay? In this sort of quantum field theory way of doing things, it turns out to be convenient, rather than using a Newtonian perspective, to use a Hamiltonian or Lagrangian perspective. And the Lagrangian is the easiest way to basically specify what your fields are, what your interactions are. And so from the Lagrangian, you derive some rules. Those rules give you numbers attached to the Feynman diagrams. And we got a lot of good questions this week. It's interesting when you get the questions because the questions are often very, very good. And they're often things that I read the question and say, well, I really should have explained that, shouldn't I have? But this is why the Q&A is important because, I'm embedded in this stuff and I kind of forget what is obvious, what is not obvious. Even if I wouldn't have ever said it's obvious, I just forget that it needs to be said out loud. So the questions have been very useful. For example, I use a lot of Greek letters, right? There are lambdas, there are omegas, there are thetas, etc. To me, everyone knows the Greek alphabet, right? Isn't this just something you learn in elementary school? But sorry about that. I actually have made hidden, translations so that I'm using fewer Greek letters than the typical particle physicist, but I do use them sometimes. Sorry about that. Learning a little bit of the Greek alphabet isn't the worst thing in the world. Okay, so I'm not going to teach you the Greek alphabet. That is not part of the Q&A, but I do apologize for using it without further explanation of what the letters are. So talking about the actual questions, here's one question. We said that this sort of Feynman diagram schematic thing where you have stuff, then you have particles coming out, this could be equal to a set of actual diagrams. Actually, since the example we looked at only had 2 particles coming out, let's just do that. We said that this could be a diagram like this, plus a diagram like this, plus diagrams like that were more complicated, that looks like boxes, okay, plus ... many, many more. The nice thing, the reason why this could make any sense at all, there's an infinite number of diagrams, is that each vertex comes with a small number attached, and therefore the more complicated diagrams count less. But so one question is, what if that doesn't quite work? What if the numbers add up to more than 1? Remember, what this is calculating for us is the amplitude. What this is calculating for us is the wave function psi of the final particles. And there will be a different value, a different complex number for psi for every possible set of final particles, by which we mean not only what the particles are, but their momenta, how they're moving off the directions and the velocities in which they're moving through space. Every different possibility comes with a value of psi, and then you square it to get the probability. The probability is psi squared for any one different possible final particle state. So the question is, what if the numbers add up to more than 1? What if psi that you get by this way, or the absolute value of psi, is greater than 1? What if you just take all these diagrams, each one of them has a number? What if you add up all those numbers and you get 1.2? Okay, then it can't be the case that the probability for any particular outcome is greater than 1. Okay, that's a greater than 100% probability that this happens. Well, the answer is, then your method didn't work. Then this idea of Feynman diagrams was not applicable. So there's two possible ways that can happen. One is you're talking about a regime of your theory where using Feynman diagrams doesn't make sense. Remember, this is perturbation theory, as we called it, which is to say, this is a way of analyzing a problem which starts with an answer that is known and exactly calculable, in this case, just particles that don't interact at all, and then adding in a little perturbation. So the assumption in this entire discussion of Feynman diagrams, etc., is that the interactions are small, are numerically very tiny. Otherwise, you're not doing perturbation theory. Otherwise, this series does not add up to a number less than 1. These numbers should be pretty small. Otherwise, you shouldn't be using this method in the first place. And that's not because, you made a mistake. I mean, it might be the case that you're in a regime where this method doesn't work. So if you're in a proton, as we've told you, as I think I've told you, is very roughly speaking a set of 3 quarks. And 2 of them are up quarks, and 1 of them is a down quark. And then there are these gluons. We haven't talked about those yet, I don't think in any detail. But the gluons are holding the quarks together. And so you might imagine that there is some set of diagrams where there are quarks connected by gluons. And indeed, you can draw those diagrams. That's fine. But you can't actually do this kind of calculation. This is a scattering calculation, okay? So you have free particles, or at least particles that are far away from each other. They come in, they interact, and they go their own way. That's very different from what's called a bound state calculation. By bound state, we just mean literally that these quarks are bound together in the nucleus. There is no regime in the proton. There is no regime in which the quarks are free particles far away from each other. We'll get into more details later about the fact that quarks have this property called confinement. They literally never are seen all by themselves. They're always in protons or neutrons or mesons or something like that. So when you have quarks, you have a bound state, and that's a reflection of the fact that, guess what? It's the strong interactions that are keeping the quarks together, and the strong interactions are strong. They are not weak. So perturbation theory doesn't work for them. Now, there is a regime, actually. So we talked about there's a coupling constant alpha for the fine structure constant for electromagnetism. There's also a coupling constant for the strong interactions. As we will see later videos, there is a regime where the strong interactions are actually weak, and you can use perturbation theory. But in this ordinary case, where you just have some quarks sitting in a proton, you have to use other techniques. These Feynman diagrams just don't work. So that's one place, that's one context in which you might get this calculation giving you a number greater than 1, and it's just because you shouldn't have been using a calculation like that in the first place. There's another case, which is more subtle, and it's way beyond the sort of intermediate level discussion that we're generally having in these lectures, but I will at least mention it. You can start with a theory, like let's say the electroweak theory. I mentioned, although we haven't done it in any detail, that Steven Weinberg and others in the 1960s proposed unifying the electromagnetic interaction with the weak interactions. They used the Higgs boson as a central idea, and this turns out to be correct. This turns out to be how the world works at the energies that we're able to probe it. So there's the electroweak theory, which, as I said, you need the Higgs boson to make sense of it. But we didn't discover the Higgs boson until 2012, and there's Weinberg in 1967 proposing this theory, okay? So for a long time, we had this theory that was very successful, but we weren't sure that it was right because we hadn't discovered the Higgs boson. One of the reasons why we were pretty convinced that either the Higgs was there or something else that was equivalent, that was just as good, that was doing the job of the Higgs, was that not only was Weinberg's theory really successful in fitting the data, but if you push it to really, really high energies, if you do calculations like this, like these Fineman diagrams, in the electroweak theory without including an explicit Higgs boson, then at high energies you start getting numbers greater than 1 for your probabilities. This was called, in this context, a violation of unitarity for technical reasons. Okay, unitarity has to do with the fact that probability is conserved in the interactions that you're looking at. And so this fact that even though the coupling constants were not large, the calculation you did using Fineman diagrams gave you an answer with a probability greater than 1 was evidence that something was wrong. And the thing that was wrong was you were trying to do a calculation in the electroweak theory without including the Higgs boson. So the fact that the unitarity, the fact that conservation of probability was breaking down was evidence to physicists, just purely theoretical evidence, that either the Higgs boson would be there when we looked at it in the Large Hadron Collider, or something else would do the same job as the Higgs boson. As it turns out, the simple Higgs boson idea was the correct one. But that's the kind of thing that can be a clue to something going on, even if you don't have direct experimental data. Your theory is breaking down in a regime where it should work, so you have to fix it somehow. So that is another way that it could break down. But the basic answer to the question, what happens if the amplitude and therefore the probability is greater than 1, is something has gone terribly wrong and you shouldn't be using these methods. Either change your theory or use different methods. Okay, another question was energy conservation in the elementary vertex for QED, quantum electrodynamics, the theory of electrons, positrons, and photons. So what I mentioned was, so we looked a lot at interactions like this, okay, where you have an electron come in, a positron come in. By the way, people asked about the arrows. It's an electron and positron coming in as time moves from left to right, but the arrow goes the other way on the positron because the arrow is not telling you the direction of motion for the positron. It's not even telling you the direction of the positron traveling through time. It's telling you the direction of electronness moving. And positrons have electronness -1. So a positron moving this way is equivalent to electronness going that way. That's why we draw the arrow that way. And likewise, over here, E minus, E plus, electron coming out, positron coming out also, and then there's a photon in between. So we looked at interactions like this, and this is, just the QED version of two billiard balls scattering off of each other, right? You have two balls coming in, they can scatter. Classically, you could figure out exactly how they would scatter off each other, what angle, what velocity. Quantum mechanically, there's more than one angle, but momentum and energy are still conserved. But what about the elementary vertex that we drew? So we drew this. Here is the electron coming in. There's a photon going out, and there is an electron going out, okay? So this is just a vertex where a single electron pops out a photon, okay? So you know that energy cannot be conserved in something like this because the electron has certain energy, and it turns into an electron plus a photon. So there must be more energy in the final state than there was in the initial state. So the question is, what's going on in this elementary vertex? And the answer is, this never happens. This elementary vertex that we put together over and over again to make real actual processes that happen is not by itself a real actual process that happens. Electrons by themselves do not just spit out photons. So another way of saying this, there's a whole set of lingo that goes along with this, right? So remember, this photon here is a virtual particle, as we explained at the end of the last video. It is not a real particle. And virtual particles don't have to have the same relationship between mass and energy and momentum that ordinary particles do. So real particles have a relationship, which is that the energy squared equals the mass squared plus the momentum squared. The momentum is a little three-dimensional vector. This is the relationship that all real particles obey. And this is actually, I'm going to give you a little bit of lingo you don't really need, but in case you run into some particle physicists on the street, this is called the mass shell. Why? Because remember we went way back when we talked about space-time. We talked about one of the nice things about the Einsteinian Minkowskian view of space-time is that it was a unification. It unified space and time, which were two separate things, into one four-dimensional concept. And along with it came other things, such as a unification of energy and momentum. Just like time is one number and position in space are three numbers, energy is one number and position and momentum is three numbers. That's not a coincidence. Energy is sort of the time-like component of momentum. That's what energy is in special relativity. So just like you can draw a space-time diagram, you can draw an energy-momentum diagram. So this can be the three dimensions of momentum. This can be the energy, okay? And there is the equivalent of a light cone. It's not a light cone, but it's a condition where, because we're setting c equals 1 here. We're setting the speed of light equals 1 in all these equations. Otherwise, the units would not work out, okay? So these diagonal lines at 45 degrees are where the energy would equal the magnitude of the momentum, plus or minus on the other side, right? So the mass shell condition, why is it called that? Why is this equation called the mass shell? Because if the energy is m squared plus p squared, it's always a little bit greater than the magnitude of p. So I'll make it a different color. But basically, this condition, e squared equals m squared plus b squared, is satisfied on a hyperbola that looks like this. This is the line that corresponds to e squared equals m squared plus p squared for some fixed value of m. It could also be negative, but we're assuming that the energies are positive, okay? So that's the mass shell, and it sort of looks like, if I could do a better three-dimensional drawing, I would fill it in up here in a sort of smooth surface of rotational symmetry, okay? And that kind of looks like a shell, maybe, I don't know. That's what it's called. It's called the mass shell. There we go. That three-dimensional hyperboloid in a four-dimensional space is known as the mass shell. And why I'm doing this, why I'm mentioning all this, is not just to give you a little bit of lingo, although that's always fun, but also to emphasize the fact that virtual particles don't live on the mass shell. Virtual particles do not have this relationship between energy and momentum. They have some energy, and they have some momentum, but this virtual particle here, this photon, its energy and momentum are just fixed by the fact that it is the combination of this electron and positron as they come together, okay? So they're not real, they're virtual, that's okay, they do not obey this mass shell condition, etc., etc. In this diagram, right here, the primary vertex, the fundamental vertex out of which we make all of the other QED vertices or diagrams, there's no way that all three of these particles, the electron coming in and the photon and the electron going out, they cannot all simultaneously satisfy this mass shell condition. They cannot all simultaneously satisfy e squared equals m squared plus p squared for all three of these particles. So these three particles cannot all be real particles. So energy is conserved at a vertex like this, but this vertex does not represent by itself any actual physical process. It can only be part of a bigger diagram. It cannot be an entire Feynman diagram all by itself, okay? So that's a great question. That's a very important point. The energy conservation means that if you have some energy and momentum coming in, the total energy momentum coming out is equal to that. So it's divided up in some way. That's what energy conservation means, and that can't be satisfied for real particles in a diagram like this. Good. I'm glad I got a chance to explain that. All right, here's a trickier question. When does the waviness of the quantum fields, waviness, how should you spell waviness? Waviness really matter? This was a good question. So what this means, I'm not sure if that's a very readable writing that I have there. Oops. Waviness. What this means is, we started by saying we have some fields. We quantized them, they were free fields, and we found that they looked like particles. Then we sort of made them not quite free fields, and we let them interact, which is very important. But we said, as long as the interactions are weak, they still were kind of particle-like. That's what enables us to do Feynman diagrams and all that stuff. But the implicit message by me making those very careful statements over and over again was that there could be contexts in which they are not like particles, right? In which the waviness really matters. So it turns out that there are a number of contexts in which the waviness really matters, in which the quantum fields really are fields. They're not really, we can't use the particle language to talk about them. They really are always fields, but sometimes we can pretend they're particles and sometimes we can't. So there's a number of different contexts. So for example, inflation. We're going to jump way ahead. This is not something that is crucially important to the level we're talking about right now, but inflation is an idea in cosmology. It has nothing to do with economics right now. This is an idea that in the early universe, there was an energy density driven by some scalar field, right? We've already talked about scalar fields. In fact, we've talked about scalar fields with a potential. So we talked about the potential looking like a simple harmonic oscillator, right? Phi squared. But the potential for a scalar field, V of phi, V of phi as a function of phi could in principle be anything. Scalar fields have some potential energy function. So let's imagine that it kind of looks like that, right? Why not? And this amount of energy, this is the amount, remember, the definition of the potential energy is the amount of energy you have other than your kinetic or gradient energy. It's the amount of energy you have just by virtue of the value of your field, not on how your field is changing from place to place. So you could have a field that has potentially an enormous amount of energy, no pun intended, and what this field would do is kind of like a ball rolling down a hill. The field really acts like this is its potential, and so it would roll down the hill like that. And if this potential is sufficiently flat, it will roll slowly. And so this energy, the energy in its potential, stays almost constant. It decreases, but it decreases slowly. So it's almost a constant amount of energy. So what we're saying here is this scalar field, if it takes a value up there on the potential, can have an almost constant and potentially quite large contribution to the energy density of the universe. Almost exactly like the vacuum energy that we have today. But because we're just making this theory up, this can be an enormously larger amount of energy, and then it can go away, right? Like once it goes down there, the energy might be very small. So the idea of inflation is, in the early universe, this is exactly what happened. You had some scalar field, it had some potential energy that was very slowly changing, and you can plug in the equations from Einstein for the expansion of the universe, and an approximately constant energy makes the universe expand exponentially, expand very, very fast. That's the phenomenon of inflation. And then you roll down the hill, and then you convert into other kinds of energy through Fineman diagrams. Your scalar field decays into quarks and electrons and photons and stuff like that. So that's the story of inflation. None of that was expressible in terms of Feynman diagrams, okay? None of that is even a story of particles. Particles, remember, go back and keep in mind the discussion we had of why quantum fields can be thought of as particles at all. We said start with free fields, take a wave function of those free fields, look at it mode by mode, individual wavelengths, individual wave vectors, okay? And then we said the height of that mode could have different values, which feeds into, once you quantize it, different energy levels as if each mode acted like a simple harmonic oscillator. So all that makes sense when you're very, very close to empty space. right? When you just have a tiny amount of fluctuation around the lowest energy state, it looks like you have a couple of particles, and they're not really interacting. Once you have a lot of particles, and they're falling on top of each other all the time, then ignoring the interactions between them is no longer a very good approximation, right? And once you have a field that is way far away from its minimum energy state, again, thinking of it as small fluctuations above the minimum energy state is not a very good approximation anymore. So when you talk about inflation, you talk about a scalar field being on a potential and rolling down and making the universe expand, the fieldness of the underlying quantum field is absolutely crucial. You really need to take it into consideration and put it front and center. That's one example. But you know what? Look, there's another example which we already talked about. The proton, okay? Inside the proton, the quarks are on top of each other. They're interacting all the time. The idea of particles, taking the quantum field and turning it into particles, we did it carefully for the case where interactions were completely turned off. And the point was, what Feynman and others showed, Heisenberg and other people showed, is that if you turn the interactions on a little bit, that language still works. The language of treating the field as particles works as long as the interactions are kind of faint, kind of weak. You can put them back in using perturbation theory and calculate their effect, but mostly you can ignore them. Think of Galileo dropping balls off of the Leaning Tower of Pisa, right? If the balls are different masses, but approximately the same size, so, you know, a ball made of wood and a ball made of steel, so their air resistance is similar, etc., you can approximately ignore the air. But if you dropped a cannonball and a feather off the Leaning Tower of Pisa, you could not ignore the difference in air. So this perturbation theory approach only makes sense when the interactions are weak and rare also, right? Not just weak, but not important for most of the lifetime of the particle. Here in a proton, the quarks are right on top of each other, they're interacting with each other strongly, and you really have to take the fieldness into consideration. You cannot treat them as small perturbations of freely moving particles. And in fact, it goes deeper than that. I'm not sure how deep we will get, but there's a wonderful story in quantum field theory about the topology of the quantum fields, the fact that quantum fields can wind around each other in interesting ways. That's something that makes zero sense from the particle point of view, but is absolutely crucial from the field point of view. So there are plenty of examples of cases where the waviness, where the fieldness of the underlying fields really does matter, where the particle description doesn't work very well. And that actually leads right into the other question that is related to this that I wanted to answer. You know, when a decay happens, think of a decay of a particle. So we didn't really do decay. So we did this fundamental vertex where the electron spits off a photon. But as I just said, this never happens in real life all by itself. It can only happen as part of a bigger diagram. So let me show you an example of a diagram where something can happen, where a particle can decay. So only one particle coming in. This will be a muon. Muon is like a heavier cousin to the electron. So it basically has all the same properties as the electron has. It has negative charge, it has the same lepton number and so forth, but it's heavier. It's a little bit more massive. And what that means is it can decay. So I'm going to give you some info here that is more than we've covered, but that's okay. It's the Q&A. We can be more casual. We don't need to be building things up piece by piece. And what can happen is the muon can emit a particle called a W boson. So this is a negatively charged muon, so it emits a negatively charged W boson. The W boson is actually heavier than the muon, okay? So this is another virtual particle. This cannot exist as a real thing. And in doing this, the muon turns into a neutrino. A neutrino is the Greek letter nu. That's the Greek letter mu. Sorry about the Greek letters there. So this is a mu. The neutrinos are nu, the Greek letters. And neutrinos come in different flavors associated with different kinds of leptons, as we call them. So there's an electron neutrino, a muon neutrino, a tau neutrino. And what it means is when you have a muon and it converts into something else, it will always convert into a muon neutrino. Again, none of this is anything you need to know. I'm just trying to give you a real-world example of the phenomenon I want to mention. This needs to be, just like the photon coming out of the electron, this needs to be a virtual diagram, because the muon turned into a W boson, and the W boson is heavier. How can that happen? Well, how it happens is that the W instantly decays into something else. So, for example, it can decay into an electron and an electron neutrino. So let me get this right. This is going to be an electron antineutrino, because we have the electronness is conserved, and the total amount of electronness at the beginning was 0. So at the end, the total amount of electronness can be 0, and both electrons and electron neutrinos carry electronness, so you can get 0 total electron number, as we call it, by giving you a +1 electron number in the electron, -1 electron number in the anti-electron neutrino. So if you count over here, this is way more detailed than I needed for this example, but this is muon number +1, and this is electron number. In the beginning, when you just have a single muon, electron number 0. This is muon number +1, because of the muon neutrino, also has muon number 1. Electron number +1 -1 equals 0. So +1 for the electron, -1 for the neutrino. Remember, this is not electric charge. The electron has negative electric charge, and the neutrino has 0 electric charge. I'm just pausing to get it all correct. You see, the let's do it this way. The electric charge is flowing down this path. Charge. Muon number is flowing down this path. And electron number is flowing down this path, if you like. It's becoming way more complicated than I want it to be. But anyway, all the numbers are conserved. There's a reason why, if you're good at particle physics, you don't have to remember what the muon decays into. You can figure it out just by thinking about it, which I basically just did, just sort of by saying, well, charge is conserved, electron number is conserved, muon number is conserved. There you go. Okay, what are we doing here? Why are we doing this? So the point is that forget about all the details. What we had in this sort of casual way we had of saying stuff happens, what we have is going in a muon, coming out a muon neutrino, oops, not an antineutrino, muon neutrino, an electron, and an electron antineutrino. So the question was, I haven't told you what the question is yet. The question was, when particles decay, when you have a particle sitting there and suddenly it, poof, turns into a bunch of other particles, is there some sense in which the particles that it turns into were inside the particle that decayed? And the reason why I'm going through all this is to make it very clear the answer is no. They were not inside. There was no electron locked inside the muon. There was no neutrinos locked inside the muon. The muon was a particle all by itself. The way that we should be thinking about this is in terms of this casual picture that we drew to start. We drew a picture where two particles were coming together, right, in space. And the point was that the particles themselves are vibrations in the quantum fields. And we were imagining that, this was an electron and a positron. Those are stable particles. Those are particles that will not decay all by themselves. But when they came on top of each other, then you had the two kinds of fields vibrating in interesting ways, and that could set up vibrations in other fields. So the quantum field theory way of thinking about particles interacting is just a language for talking about fields being on top of each other and changing each other's vibrations, okay? The same thing can happen if you just have a single particle. So if you have a single particle, like this is the muon, a muon is not a stable particle. And basically, very roughly speaking, again, this is probably getting ahead, but how do you know if a particle is stable or not? Well, you have these quantities that are conserved, like electric charge, like electron number, like muon number, And particles that are heavy want to turn into particles that are lighter. In fact, this is actually secretly an expression of the second law of thermodynamics. This is one particle turning into three. There are more ways for particles to be in collections of three than for particles to just be one. So by having the one particle decay into three, it increases the entropy of the universe. There are more ways for that to happen. So when you have a heavy particle, it will try its best to decay into a collection of lighter particles. It can't decay into even heavier particles because that would violate energy conservation. Sometimes it cannot even decay into lighter particles because it would violate something else, charge conservation or muon number or something like that. The proton, as far as we know, is a stable particle, even though it's heavier than the electron and so forth. You might say, why can't a proton decay into a positron, an anti-electron? That would conserve electric charge, but it violates something called baryon number. A proton is a baryon, it has a conserved quantity also. So that's why it can't decay. But the muon, it's very happy to decay. The muon can turn into these other particles. But it really is converting into these other particles, okay? The muon does not have an electron and neutrinos locked up inside it. What it's doing is it's a field, it's vibrating, and it can set up vibrations in those other fields. So this muon turns into three particles going their own way, two neutrinos and one electron, and it satisfies all the conservation laws. So basically, it's just how long does it take for the vibration in that muon to be observed, to be converting into these other vibrations. If you were truly quantum mechanical, if we weren't sort of locked in our classical intuition, all the fields are always vibrating. But when you observe it, it's just like when you observe any other wave function. You're going to get an answer when you observe it. So when you observe the particles, it will either look like a muon or it will look like an electron and two neutrinos, okay? Really, it's always a combination of both. It's a superposition because we're doing quantum mechanics. But when you make that observational measurement, there's a probability you will get one answer versus the other. So no, they're not different constituents locked inside the decaying particles. It's just bringing to life other particles by interacting with their underlying fields. Good, that's a very important thing. Okay, two more little topics that are kind of fun. One is locality, because, and this is a fair cop, someone caught me on this, I think, because I was a little bit ambiguous talking about locality. Remember, we first talked about locality in the context of Newtonian mechanics, I think, when we talked about space. If you go back to the video about space, and we talked about the fact that, well, we talked about the Hamiltonian point of view on fundamental physics. I won't write it here, but the Hamiltonian is a perspective that says that positions and momenta are both equally fundamental, but you can derive the equations of motion. And then one of the equations of motion says momentum equals mass times the velocity, okay? So that's how velocity relates to this fundamental thing we call the momentum. But clearly, space and momentum, location and momentum are different. We think that we live in space. We live in position space. Nobody thinks we live in momentum space. And we said, well, the reason why is because space is the set of variables in terms of which interactions appear local. Billiard balls bump into each other when they're at the same point in space. They don't bump into each other when they're the same momentum in any sense. So even though the formalism of Hamiltonian mechanics puts position and momentum on an equal footing, the real world treats them differently because of what the Hamiltonian, the real world actually is. In the quantum field theory, or even classical field theory context, if you have some Hamiltonian, we write the Hamiltonian in principle as a function of positions and momenta. But for field theory, the Hamiltonian is going to be an integral over space of something called the Hamiltonian density, which is going to depend on the field and the momentum conjugate to that field, okay? And these are, just to be super duper duper clear, these are both functions of space. So what I mean by this is phi of x equals the field, the actual value of the field, so it's the field configuration, and that is analogous to x in a point particle, whereas pi of x is the field momentum, And that, guess what, is analogous to the momentum of a point particle. So we have a Hamiltonian density, which is a function of the field and its conjugate momentum, and then we integrate it over space. So remember we said it is not something like h equals an integral d3x d3y of, phi of x times pi of y. That would be some weird thing where the field at one point in space and its momentum at a different point in space were interacting with each other. That is not what it is. That is not what happens. The field and its momentum, or the field in itself, only interact at the same point in space. That is locality in the context of field theory, whether quantum or classical. The field interacts with itself or other fields only at exactly the same point in space. That's what locality means in that context. Now there's another context in which we talk about locality, which is the spooky action at a distance, right? Remember Alice and Bob and their entangled particles? So Alice and Bob can have a wave function for two entangled particles that looks like 1 over the square root of 2 times 2 particles up, spins up, plus 2 spins down. And then we know that if we measure Alice's spin and it's up, Bob's spin will instantly be down, or vice versa. Sorry. The way I wrote it here, if we measure Alice's spin up, we know that Bob's spin is going to be up, and likewise for down, okay? And that's true even if the two particles are very, very far apart. So that is what Einstein didn't like. He said it's spooky action at a distance, etc. But so in my book, Something Deeply Hidden, I gave names to these two different kinds of things. I said that there is dynamical locality. So in other words, when you have the equations of motion, whether the classical equations or the Schrödinger equation, the equations of motion for the wave function, or for the fields that make up the wave function, are local. And that's what is encoded in this fact, that the Hamiltonian is a function of space, not different points in space interacting with each other. But you have measurement non-locality. And that's what Einstein was complaining about. So this is just as true in quantum field theory as it is in point particles or spins or qubits or whatever. In quantum field theory, you can in fact have things that are entangled with each other, and therefore when you make a measurement at one point in space, you're going to be able to say something about what's going on at another point in space far away. That's the non-locality of the measurement process in quantum mechanics. Remember, when we first talked about quantum mechanics, we said there are rules for what the wave function does when you're not looking at it, and there are rules for what the wave function does when you look at it. So the point is, all of this song and dance about locality in field theory is all in reference to what the wave function is doing when you're not looking at it. The dynamics of the wave function under the Schrödinger equation. When you look at it, when you measure it, there's just as much non-locality in quantum field theory as there is in ordinary quantum mechanics. It's exactly the same story. So there's nothing different here in quantum field theory from ordinary quantum mechanics. In both cases, you have the dynamics of the things when you're not looking at them, which obey some principle of locality. Interactions happen when things are at the same point in space. And you can have non-locality because of quantum entanglement. Both things are true. So typically, I will admit, people who talk about locality don't tell you whether they're talking about dynamical locality or measurement locality. Okay, so if you talk to someone whose interest is in the foundations of quantum mechanics, and they say quantum mechanics is non-local, they mean that there's measurement non-locality, Bell's theorem, EPR correlation, things like this. If you talk to a quantum field theorist who says physics is local, what they mean is that it's dynamically local. They're not really caring about the measurement problem as much. So both are true. They're just different words. They're the same word for two different things. All right. Last thing I wanted to mention is the number of degrees of freedom. This is an interesting question that was brought up in the questions. In a quantum field theory, how many degrees of freedom are there? Degrees of freedom are just things you need to specify to tell me what's going on. That's what a degree of freedom is. It might correspond to some physical thing, like the position of this particle is a degree of freedom, or it might be more abstract. There's just some quantum mechanical degree of freedom that goes into specifying the state of the physical system. Well, in quantum field theory, the answer is clearly infinity. There are an infinite number of degrees of freedom. But it's still an interesting question to address because there are different sources of infinity. So let me be clear here. There's an uninteresting sense of infinity in this case, which is if you just have infinity times infinity, or infinity plus infinity, you still get infinity, okay? That's what you're going to get one way or the other, but it's not any bigger. Infinity plus infinity is the same infinity that you had when you added the two infinities together. There's a whole complicated, well, not really complicated, but subtle and careful mathematical analysis about how big different kinds of infinities are. There are more real numbers than there are integers, even though they're both infinitely big. But when you add them together, you get whatever the biggest infinity is. You don't get a bigger infinity than you started with. That's not what we're talking about here. That's not what I'm going to worry about here anyway. Whether the infinities we're talking about are discrete or continuous, etc., is not what I'm interested in. What I'm interested in is why are there infinities at all? So there's actually three different sources for there being an infinite number of degrees of freedom in quantum field theory, and they're all kind of important and kind of different, okay? So one source of infinity is that space is infinite. That is one reason why there's an infinite number of degrees of freedom. Just imagine that you have space and you divide it up into little subregions, okay? And you can, remember we said, in one of these videos, I don't know, I've done a lot of videos. It's in lockdown. I can't remember which video we talked about, but I think it was the Q&A it was the Q&A for fields that I talked about the entanglement structure of empty space, of the vacuum for quantum fields. And I said you could divide up space and you could say, well, here's what's going on in that region of space, here's what's going on in that region. I said they're entangled, etc. So if I did that, even if I only had 1 degree of freedom per region of space, there's an infinite number of regions of space, right? So that's a sort of simple and cheap infinity. This would be, because it's large distances, large amounts of space that are contributing this infinite number of degrees of freedom. This is what is called an infrared divergence, if you like. It's not quite... I'm abusing the notation a little bit here, but this is simply because space is big. This is like saying if I have an infinitely big universe with a finite number of particles per cubic centimeter, I would have an infinite number of particles, even in classical mechanics. So that's a kind of infinity, but it's not a specifically fundamental quantum mechanical or quantum field theory kind of infinity, okay? It's just because space is big. So we can say, let's look at a box. Let's look at a box of finite size. This is called putting an infrared cutoff on our theory. We're only going to look at a box of finite size. So here is, by a box, I just mean a region of space. I don't mean a physical box. You don't need to bring cardboard or wood out or anything like that. I mean just consider, hypothetically, in your brain, a region of space with some fixed size, let's say L. We're not going to go into any details here, but we're going to get rid of the annoying infinity because space is infinitely big by asking how many degrees of freedom are there in a box, let's say 1 centimeter on each side, okay? Well, guess what? There's an infinite number of degrees of freedom inside the box, and that is because there are an infinite number of wavelengths that you can fit inside that box. So I can have, I can fit this kind of wave inside that box that has sort of one full up and down wave from one side of the box to the other. I can also fit this wave inside the box that does that twice. We can talk about whether or not you want to fit half integers or whatever inside the box. But the point is, I can just keep going. I can make all sorts of wavelengths and put them inside the box. And you can't stop me. And I can make the wavelength that I consider smaller and smaller and smaller until it goes to 0 size. So if I count how many different wavelengths I can fit in the box, there are an infinite number. So there are an infinite number of distinct modes in a box. So infinite number of modes in any box of size L. So that's an infinity, and that is a more interesting infinity in some sense. It's not just because space is big. This is now an intrinsic feature of quantum field theory because it comes from starting from the assumption that we have an infinite number, that we have a field that is smooth and continuous, okay? That's redundant, a smooth field, that is to say, a field that exists with a different value at literally every point in space, and that space itself is smooth. So the field is defined at an infinite number of points. Therefore, if you decompose it into wavelengths, there are an infinite number of wavelengths. And this, I say, is more interesting because here you might begin to doubt that you actually believe what quantum field theory is telling you, right? We haven't added gravity into the game yet, but when we do add gravity in, there'll be something called the Planck length, after Max Planck, the German physicist, who used his new constant of nature to make these fundamental units of energy and mass and time and so forth. Without gravity, if gravity is not important, Newton's constant does not appear in the game, and you can't make the Planck length. You can't construct that number without Newton's constant. So if you're just doing quantum field theory without gravity, which is what most quantum field theorists do, right? All particle physicists, they just ignore gravity. There's no such thing as the Planck length, and quantum field theory by itself extends down to arbitrarily small wavelengths, down to 0 wavelengths. And remember, wavelengths are inversely proportional to energy, right? Very roughly speaking, the energy of a mode goes as 1 over the wavelength. I say very roughly because there are 2 pi's that I'm not going to get right. So modes become higher and higher energy as their wavelengths become shorter and shorter, and there are an infinite number of them that you can talk about. But you might suspect that once you include gravity, once you admit that gravity exists in the real world, this infinity might go away, right? This might be an artifact of taking quantum field theory seriously in a regime where you shouldn't be taking it seriously. So that's why it's a more interesting infinity, because it's a little more problematic. It's a little bit less certain that it exists in the real world. I mean, there's the formalism of quantum field theory that we use to do calculations and we trust in a certain regime. But then there's what happens in the real world outside that regime, okay? And quantum field theory says what happens, but it might not be right. It might not be correct. So this is an infinity, this is a source of an infinite number of degrees of freedom that may or may not be part of the real world. So you could say, okay, let's put so consider a smallest wavelength. In other words, let's just say by hand that we are only going to consider wavelengths between, what should we call it? We said lambda, we used L, I used all the good letters. K, I don't know. K, this is a wavelength, okay, and it is the smallest possible wavelength. So all real wavelengths are between the size of the box and this tiny little number k. So in other words, I'm now considering a box which has a size L across. Ooh, my boxes are getting worse and worse. But there's also sort of a smallest possible sub-box inside, okay? And this has size k across. I shouldn't use k because k is what we used for the wave number, right? What is a number that we haven't used yet? Hij, k, J. There you go, J. People usually just use subscripts for this, but I'm trying to avoid subscripts as much as I can. So I'm just inventing this. This is not part of quantum field theory. I'm just saying let's contemplate what happens. Let's contemplate when we have a smallest wavelength we will allow ourselves to contemplate. Maybe it's the Planck length, but we're just being open-minded. We're saying there's a smallest possible wavelength. And there's a largest possible wavelength because we have a box that we're considering. So you might think now that there's a smallest wavelength and a largest wavelength, there's a finite number of wavelengths that I need to consider inside the box. Therefore, there are a finite number of degrees of freedom. But that's wrong. That's still wrong because there's a third source it's a third infinity, which is that each mode is a simple harmonic oscillator, right? Or is mathematically equivalent to a simple harmonic oscillator. And what that means is, just to be super duper clear here, pick a mode of a certain wavelength, certain fixed wavelength, let's say this one, okay? So that is a wavelength smaller than L, but larger than J. So the wavelength here is this, okay? Starting from here and going back to the same point. So this is an allowed wavelength, therefore it's an allowed mode, but what we showed is that the quantum mechanical description of that mode is equivalent to a simple harmonic oscillator, which means that that mode of fixed wavelength has a lowest energy state, it has a next highest energy state, a next highest energy state, and an infinite number of energy states, okay? So every mode has an infinite number of energy states, and that implies an infinite number of degrees of freedom. So this is a third way. How many do we have here? Yeah, a third way in which you can get an infinite number of degrees of freedom in quantum field theory. There's an infinite number of places the thing could be. In any one place, in any one box, there's an infinite number of wavelengths the mode could have. And for any one wavelength, there's an infinite number of energies that it could have, because it's like a simple harmonic oscillator. Now this is also something that you might begin to doubt in the context of gravity. Because if you have a box of fixed size and you put an infinite amount of energy in it, or some very, very large amount of energy in it, it will collapse to make a black hole. And black holes, whatever we might know about them, black holes are not simple perturbations of flat space-time, okay? Black holes are probably not even described by quantum field theory at all. This is why quantum gravity is difficult and subtle, and you need to go beyond simple-minded quantum field theory to do quantum gravity. So you can put another cutoff, you can put an energy cutoff, which was sort of invented by Jacob Bekenstein, the Bekenstein bound. He phrased it in terms of an amount of energy, but it's the same basic idea. He said, don't include energies for wavelengths such that the amount of energy in the box would make a black hole. There's a cutoff there as well. Again, we don't know if that's true or not. I mean, this is right at the edge of what we understand in modern physics. You know, we understand this. Okay, space could be big. Let's imagine that we just look at space piece by piece. But here, for the number of wavelengths, the smallest wavelength, and the amount of energy per wavelength, these are different phenomena that only come up when gravity is important. And we know that gravity is important, but we don't know what to do about it. We don't have the once and for all final quantum theory of gravity. So we make these sort of haphazard guesses, or we try to invent a quantum theory of gravity. You could try to do string theory or loop quantum gravity and say that within those theories, there are specific answers to these questions. But we don't know which theory is right. So we don't know what the final answer to these questions are yet. So anyway, long story short, in quantum field theory, there are an infinite number of degrees of freedom, not just overall, but even in any one little sized box. And that is a clue that quantum field theory is not the final story. That quantum field theory is not the way that nature works at a fundamental level. I want you to be able to hold these two ideas in your head at the same time. Quantum field theory is the best theory we currently have of the way nature works. And quantum field theory is probably not the way nature works. This is part of this story that I've said before, that we're in a situation where we have theories that fit the data really, really well, but are not the final answer. That's why physics is not done yet. That's why we have to keep going. That's why it's important to inspire new generations of young people to think about these big ideas, because I'm optimistic that eventually we will figure this stuff out.